Hello, everyone. I apologize for not being here in person, but I hope you will still enjoy my presentation. In this talk, I will present two Rails bugs, one from about 10 years ago and another one from just a few months back. And for each bug, I will go over how I debug them, how I fix them, and finally reflect back on what I believe can be learned from it. But first, let me introduce myself. I'm Jean Boutier, probably better known as byroot. I'm a member of the Rails core team as well as a Ruby committer. I also maintain a number of popular gems such as Redis, Bootsnap, or MessagePack. And professionally, I work for Shopify on their Ruby and Rails infrastructure team. When I work for that team, you usually will see me interact on GitHub as Casper is fine. I do a bit of everything, but my focus is mainly on performance and stability. The first bug I'd like to present, which also happened to be my first sizable Rails contribution, was almost 10 years ago and is regarding counter caches. But before a bit of context, at that date, I joined the newly created Shopify office in Montreal, and Shopify was growing a lot at that time, so we always had new team members in the office, and I often didn't really have something to do explicitly told. So I just started fixing bugs I could find on all issues on GitHub and things like that, until one day my boss, my lead, mentioned a slow database query issue. The way we were finding slow queries at the time, and probably still today, was through the MySQL slow query logs. So every time a query would take longer than a certain threshold, it would be logged, and we would have reports from it. And in this instance, it was a count query that was counting products inside product collections. And it was taking, like in this instance, taking 126 milliseconds, which is a lot of time. Even though it was done from a background job, it's still a lot of stress to put on the database that we don't want. So first I need to explain a bit the usual way you avoid slow count queries is with Rails is to use active records counter caches. It's a fairly simple denormalization techniques. You just create a column on the parent model, and Rails take care of incrementing and decrementing that column whenever you create or destroy a record. Under the hood, it uses atomic queries to prevent race conditions. So in the same transaction in which you create a record, it just emits a query to atomically increment the counter. And when you delete a record, it atomically decrements that counter. So I went to look for where the query was coming from, and I saw that it wasn't using a counter cache, so I thought I would just add one. But then when I went to add one, I noticed that it already existed. There was already a counter cache. So I used git blame to figure out where this line of code was coming from. And turns out that barely 6 months prior, someone changed that line of code to stop using the counter caches. So clearly there was more to this problem. It wasn't such a simple fix. By following the issues inside GitHub and following the threads, I managed to find an even older issue that was mentioning some desynchronized counter caches. Like some of our customers in our interface would see collection reporting having negative amount of products in them, which obviously is not possible. There was some other PS that have been attempted, some like moving those counter caches to Redis and things like that, but none solved the problem just yet. So my colleagues resorted to go back to a count query. In my initial assessment, I didn't believe it could be a concurrency issue because that was what previous people trying to fix big bugs assumed and failed to do so. And I was also very confident that active record atomic incrementation was very sound, like very foolproof. And counter caches had been in Rails pretty much since the very first version. So surely someone would have noticed such a bug a long time ago if it existed. So the next step was to go look at the implementation to see what else it could be. So I started to look at how they're implemented to try to see if we were misusing them somehow. And as you can see, the code is rather cryptic because it uses a lot of metaprogramming. But if we remove the metaprogramming layer, the logic is actually quite simple. Here's a simplified version of how they are implemented. As you can see, it used simply two active record callbacks. And so after a record is created, it invokes the incrementer. Before a record is destroyed, it decrements. So my first thought was that since it used model callbacks, perhaps we were doing updates without, like by bypassing the callbacks triggering. But a careful audit of the application didn't reveal anything like that. So I was back to square one. I had no idea what was going on. So I went to analyze the data I could see, and looking at the 40 records in production, the desynchronized caches were always lower than what they should be, never higher. So the issue, logical conclusion, but the issue was on the destroy code path and not on the create, or on both. So perhaps it was a concurrency issue after all. So I went to try to reproduce the problem in isolation. So I created a minimal Rails application from scratch with a similar counter cache setup, even a bit simplified, and set up with Unicorn with 8 processes, so I could have like a good amount of concurrency even in local. And so I did the general Rails scaffold thing, and I just created a few products, and then I messed around for a little bit until I had the idea of clicking very, very fast on the same destroy button to try to see what was going on. And suddenly I was able to reproduce the bug. I had, as you can see up there, the counter cache indicates a single product, but I have 2 listed under it. So it was exactly what we were witnessing in production, and it was indeed a concurrency issue. So the next step was to try to understand better in detail what happened. But since I could reproduce locally, I could observe it and reproduce it and observe it as much as I wanted. I could add any logs I wanted and things like that. But the first thing I looked at was the Rails log to understand the course of events, what really was happening. And here you actually have like the explication of the bug. I highlighted them in red and blue. Those are like 2 Unicorn processes. And you can see that the red process loads the record, then the blue process also loads the same record, and then they both issue delete queries, and they both update the counter. So 2 processes were able to destroy the same record without failing. Now that I understood that, I was able to reduce the reproduction even more. And you can just do it with like a very simple Ruby code in the same process. You don't even need 2 processes. You can just load the same record twice and then destroy it twice. And so now that I had like such a simple reproduction like that, I could do the same and directly go in the MySQL command line. And that's where it hit me that the MySQL delete statements are what we call idempotent. So it will succeed, like even if it happened again, you can repeat it and you're gonna end up with the same results. The record will stay destroyed. I wanted to figure out a fix for it, and the best way to work on a fix is usually to have like a good feedback loop, like a fast way of reproducing and testing things. And so the ideal solution for that is to write a test case, obviously. And worst case, if I couldn't figure out the fix myself, that would make for a very good bug report on Rails. But before I look for bug fix myself, I search for prior pull requests and issues about it, because such a big bug, certainly someone else must have run into it. And I found an old PR that unfortunately wasn't merged, but the reason it wasn't merged is that it was trying to use locks, which has a very detrimental effect on performance. It created a lot of contention in the database. So if I wanted this bug to be fixed in Rails, I needed to find a more efficient solution. And that's when it hit me that previously, when I was messing around in the MySQL shell, the answer was right under my eye. As you can see here, we can see on the first query that MySQL tells us that one row was deleted. And when we repeat it, it says that no row was deleted. So if we could access this information from Ruby, we could simply not issue the decrement if no record was impacted. We would be good. And so it turns out that this information, we add it in Ruby if you call the delete all method on a relation in Rails, you will actually get an integer back, which is the number of affected rows. So it was just a matter of all wiring it together and to make it work. But the problem is that since counter caches were implemented as model callbacks, it was very hard to get this information because callbacks are run a bit in isolation. They don't receive parameters. They cannot read anything. So the first thing I did was to refactor them to be a first-class feature, to no longer be inside callbacks, but to be a regular module in active record that just is executed before and after create and destroy. And then it was just, once this was done, it was just a matter of adding a simple condition. Did we affect more than one row of 0 rows? Then we can decrement. But like this worked in test and all, and I was happy with it. But before submitting the fix to Rails, I wanted to first test it in production because I wanted to be sure it would work at scale, not just on my machine. And I also didn't want to wait for the next Rails release to be able to fix this bug in our application. And perhaps this wasn't the only bug, right? Maybe this would reveal that there's a second bug lurking behind. So I first implemented the fix as a monkey patch that I could apply on our application. I let the monkey patch run in production for several weeks, and I was regularly checking, like doing queries to make sure, like to try to find desynchronized counters. And a bit to my surprise, there was, after weeks, I couldn't find any single desynchronized counter. So I was able to re-enable the cache and make that slow query disappear. Now that I had a fix, the next thing was to contribute it back upstream because maintaining a monkey patch is pretty annoying and painful. And also, there's no reason not to fix Rails, right? Some other people are experiencing this bug. We might as well share it with them. It felt really, really good submitting like a clean solution for such a long-standing bug. It has been plaguing Shopify for over a year now. The person, like the Rails core member reviewing my pull request ended up being Aaron Patterson, Thunderlove. However, it didn't go as I imagined. His response seemed like he didn't properly understand the bug nor the fix I created. I was a bit destabilized. So I answered quite stupidly. My English and communication skills in general weren't that great at the time. So now that I maintain many projects, including Rails, I better understand how this dynamic works. Maintenance can be wrong, especially on large projects like Rails, where there isn't a single maintainer that either wrote or reviewed all the code. Sometimes they discover the code just as the same time you're submitting the pull request. I also just spend like days thinking about this problem, or days, weeks. And Aaron had much less fresh context on the feature and issue than I did. And so when you identify and fix the bug, you already is full of context, and like your job and the challenge is to identify the relevant information and writing down in the PR to share with the maintainer. I didn't do a great job of that. I just assumed that the problem and solution were obvious because it was so fresh in my head. But lucky for me, Aaron is a really nice person, so he just joked about my blunder. Many maintainers wouldn't have taken it so well, but the PR was ultimately managed, as well as a couple cleanup follow-up, and that was my first major Rails contribution. So what I think we can learn from this is first the debugging technique I use, which is, pretty much a scientific method, right? You theorize about what it could be, and you make an experiment to try to confirm that. And if it works, then great, you have found your bug. If it didn't work, then you have learned more that allows you to make another theory on what was going on. It doesn't have to be followed very, very strictly, but sometimes with knowledge or intuition, you can directly go to the bug. But when you don't know where to start, this is extremely helpful. Another thing I would like to mention here is this taught me that your dependency is like code that has been written by a colleague. Like maybe your colleague is in vacation or left the company. It doesn't matter that you didn't write it or someone else write it. You should be able to debug it and fix it yourself if need to. And to me, open source and like your dependencies is the same thing. Like it has been written by other contributors, other maintainers, but you should be able to debug it yourself and submit a fix or at least a good bug report. That also implies that it shouldn't necessitate any kind of authorization from a manager or anything. It's just like you're running a library in production, debugging it is just like debugging your own code. Another important thing I think is like the step one of debugging is to get a raw production. Unless it's really a trivial bug, you're not gonna get anywhere until you can reproduce the bug. And the faster you can reproduce it, the better. It means the more iteration where you be able to theorize, observe, and etc., etc. And worst case, if you can find a fix yourself, that reproduction will be tremendously helpful for the maintainers, and people with more context will probably be able to fix it. And lastly, communication is extremely important. It doesn't matter if you're right. If you come off as rude or whatever, you won't get your ways. It's very important to be nice and agreeable in addition to be right. And actually, it's even more important. Make the maintainer want to help you. There's no point being right if nobody would bother listening to you. Which leads me to the second bug I would like to present you, which is from earlier this year in March. In between, like there was 10 years. And since then I became a Ruby committer as well as a Rails committer and then later Rails core member. I'm still working at Shopify on the Rails, Ruby and Rails infrastructure team, which didn't exist back in the day. And bugs don't scare me anymore, so I thought this one you'll see is quite a theory. So I was just reading Ruby Social, which is like a Mastodon instance, like some kind of open source alternative to Twitter. And I saw a post from someone asking help with a bug in the source code of Mastodon itself, because it happened to be a Rails application. I had a bit of time in front of me, so I figured I would have a look and probably just wrap this up quickly. The Mastodon application had recently been made compatible with Ruby 3.2. It was done by Aaron Patterson because he wanted to be able to test widget, like latest widget developments on Mastodon. And some users upgraded to 3.2, but when they did, they started experiencing errors in production. I just glanced down the backtrace and saw like, reading an attribute on the model is failing with like a no method error on nil. So most likely I was like, okay, this is simple. It's trying to access the ID of an active record instance, and probably this instance doesn't have an ID. So since I didn't have a lot of time in front of me, and I was quite confident, to be honest, overconfident probably. So I assume they simply run in small limitation, and I gave them a quick way to work around it. And I pledged to do a small pull request to add the feature so that it will solve their problem in the future. But when trying to implement the fix on the Rails side, I quickly realized I was totally off. I ignored many clues that were in the thread, and I jumped to conclusion way too quickly. I rewinded back and went to look at the source code, and I noticed that the problem wasn't that the model didn't have an ID column, like I said, is that it was trying to access the ID of the model, ID being just one of the many attributes of a model, before the attributes were loaded, which was way more weird than I thought. Another interesting tidbit that another user shared on the thread a bit later, and which is an important clue I had been ignoring so far, was that this issue would only manifest itself on Ruby 3.2. So any explanation that didn't include a change of behavior between Ruby 3.1 and Ruby 3.2 wouldn't cut it. It had to be a change in how Ruby behaves. And since the bug was triggered by Marshall, by loading a record from cache with Marshall, I went to look for suspicious changes in the Marshall implementation. So since I'm a Ruby committer, I'm also able to navigate the Ruby codebase relatively easily. And so I went to look for all the changes in the Marshall implementation between Ruby 3.1 and 3.2. I was hoping to find like a big, clear thing, but nothing was jumping in my eyes. And to be honest, from experience, looking at Git log is always a disparate move. Unless you know that the change happened in a very small time frame and you're looking at a dozen commits or so, you're never gonna find a bug you don't understand yet by looking at the Git log. You first need to understand the bug, and then you can find what introduced it in the Git log. So at this stage, I had I had a better idea of what was happening, but it still wasn't enough to reproduce myself. So impossible for me to investigate any further. So I just waited for users of the Mastodon, like people who host Mastodon, to report more information. The next day, another user posted a very interesting observation. They tried to load a broken Marshall payload from Ruby 3.1, and it was failing the same way. So before that, we were convinced the bug was in Marshall, but we didn't know if it was loading the record that was broken, or if it was generating broken records that then couldn't be loaded. Thanks to this observation from this user, we knew that the bug was in Marshall dump. Ruby 3.2 was generating invalid payloads, but both versions were correctly trying to deserialize. So at this stage, the main thing preventing me from going deeper was to get my hand in one of those corrected payloads so I could just try to understand what was wrong with them. Because I knew they were broken, but I didn't know what was broken in them. The problem is that this cache contained a lot of personal information, and Mastodon is pretty tight on like not leaking personal information and things like that. That's the whole point of a decentralized system. So those payloads couldn't be shared with me without first anonymizing the data, which make everything more complicated. But soon after, I got the next best thing, which is someone used some kind of decompiler to just change Marshall is a binary representation, and they use the decompiler to make some kind of like more Ruby source code style representation, which allows them to strip all the private data in it and to just share the structure with me. So I couldn't directly use it to reproduce the error, but I could still look for more clues in it. And one of the clues we can see here is that symbol link entry, which is a mark for a circular reference in the payload. And that circular references are usually a source of problems. So this circular reference, the presence of this circular reference allowed me to formulate a new theory. My new theory now was an active record instance is being used as a hash key in a circular way. So here's a teeny code snippet to showcase what I thought was happening, is that if you allocate an active record instance, but without initializing it. So here we don't use new, we use allocate. So the initialize method is not invoked. So it doesn't have any instance variable defined. And if we try to insert it in a hash as a key, the Ruby will call the hash method on it, and it's going to fail exactly as the same way as it was reported in production. So now I had a good idea of what it could be, but I needed to understand how we could get there. And so to better understand that, we need to better understand Marshall. And the key thing to understand about Marshall is that it doesn't load objects atomically. Like from your point of view, you're calling a single method and it returns you an object graph all in one shot. But internally in the Ruby virtual machine, it actually first allocates the object and then assign the instance variable one by one, like it's all sequential. So there is points where the object exists and is not yet fully initialized. And because of this, in case of circular references, Marshall may have to insert a partially initialized object as a hash key. And that automatically calls the hash method on the object to be able to know where to store it inside the hash. And such a scenario would perfectly explain our bug. So now I was searching for a pattern. I needed to find a place in Active Record where an Active Record instance could be used as key. So lucky for me, I know Active Record relatively well. And so I immediately suspected that it was the association cache, which is an instance variable that stores the loaded record. When you load the following an association, we load the associated record and we store them on the parent. So this would explain it, but we would need to be in a case where, for this bug to reproduce, we would need to be in a case where Marshall loads the association cache before the attributes of the record. And the way Marshall serializes the attributes of an object is that it simply respects the order you see when you query the instance variable of an object with object instance variables. And this couldn't explain my bug, because if you are to look to instantiate an active record and look at its instance variable, the attributes property is defined before the association cache. So either this wasn't it, or either in some cases the order will be different. And so to understand how the order could be different, we have to look at, well, how the order is defined in Ruby. So At the surface, it's quite simple. Here you can see two classes with two instance variable each, and they define in reverse order. So you can see that A has like variable A and B, whereas the other class has variable B and then A. It simply preserves the insertion order, just like a hash would. But there's more tricky situations. In the first example, we were using two distinct classes, but what if the same class sometimes defined in one order, sometimes in another? Well, it happens that this changed recently. The Ruby committer Slack has a very helpful bot, which is called allruby, and you can give it a snippet of code, and it's going to execute it on all the different Ruby versions and show you what changed over time. And here we had like a huge smoking gun because we could see that on Ruby 3.2, the order changed. Back in 3.1, the order was the same for all the instances of a class, whereas in 3.2, each instance has its own order. This was caused by the introduction of object shapes. And I happen to know object shapes pretty well, given they were implemented by two of my teammates, Aaron and Gemma. And I reported a few early bugs to them, so I had to dabble in it quite a bit. But until I worked on these Rails bugs, I never realized that shapes will cause this semantic difference in Ruby. But to be honest, the instance variable ordering in Ruby is an implementation detail. It's not specified anywhere. It can change at any time. And like Ruby and Gemma changed it and they didn't break any tests because, well, it wasn't specified. So I went to search for a pattern again, but this time I was looking for a place where we would assign association cache before attributes. That would cause the order to be different. And yet again, I found another smoking gun. Since I knew the two variables important variables were attributes and association cache, I grabbed for all the places where they were assigned. And I found that when you duplicate a record, we first assign the association cache and then the rest. So everything works fine, but if you dupe a record, then you may be able to create corrupted caches. So I went to use a Rails console. Like all this time, I had like a Rails console loaded in Mastodon and trying to reproduce it locally so I could better understand. And I just duped the record and it actually created the situation. I was like ecstatic, as you can see by the number of exclamation points. I've been searching for this bug for 2-3 days by then, like not full time, of course, but it has been obsessing me quite a bit. But I quickly realized that my reproduction was just by chance. I just had this console open for so long, but I tried so many things that things were different, and I tried to do it again and it wouldn't reproduce. That's where it hit me that it wasn't just a shape issue, it was a shape too complex issue. So to understand what shape too complex is that object shapes are an optimization that allow accessing and setting instance variable much faster in most cases. But the problem is that since they rely on insertion order, each unique insertion order creates a new shape. Some code that inserts instance variable in random order could create an explosion of the number of shape and destroy performance. So to counter that, when a class starts to have more than 8 leaf shapes, it's tagged with a property that's called shape too complex. And when this happens, it reverts back to using a hash internally to store the attributes. And so that's why the bug was so hard to reproduce. It would only happen after the application had run long enough to cause too many shapes on that class. And so you would need to let the application run for quite a while before it happens. So now that we knew what the bug was, we had to fix it. And so arguably the bug is just in Ruby and we should just fix there. But I accepting that Rails 7 was incompatible with the latest Ruby version. And Mastodon user would needed a fix, right? And also Rails.cache relying on such undefined behavior was a liability. So to me, it was a conjunction of two bugs that had to be fixed in two places. But just before that, it just hit me that at Shopify, we had been running Ruby 3.2 for over 3 months now, and we never ran into that bug. And the reason was because we replaced Marshall as a serializer for Rails cache for this kind of reasons, actually. Not this one specifically, but for many other possible errors with it, because it makes it way too easy to store data that you didn't quite expect to store, didn't quite realize what the constraints are when you store them in cache. So instead, we used a custom serializer defined in a gem called Paquito. And so the proper short-term fix for Mastodon was to integrate Paquito, or at least something very similar. So I went to implement, basically I didn't want to force the dependency on Paquito to Mastodon. So, and I wanted something easy to monkey patch. So I implemented something that works in the same way, but much more simplified. Without going too much into details, rather than give the whole object tree to Marshall, I first do a path to convert it in simple objects so that I can control the order and reconstitute the object hierarchy manually so that I don't end up with those circular reference issues. And the Mastodon maintainer just merged it, and as a side benefit, the payloads, so the size of the cache entries ended up 47% smaller, like let's say half as big. And unsurprisingly, they were also like twice as fast to generate, because Marshall performance is very much linear with the size of the cache entries. The reason is that if you just give an object like an active record to Marshall, it's going to serialize all the internal state, most of which is like just temporary cache. You actually don't need to persist. All you need is really just the attributes and whether it was persisted or not in the database. So most of that payload is actually useless. And now that Mastodon had a monkey patch and we're happy with it, it was time to fix Rails so that other apps don't hit the same bug. I applied a similar technique, but a bit more advanced. Something that not everyone knows is that Marshall objects can define a special method called Marshall dump and another one called Marshall load that allows it to control all their serialized in Marshall. Rather than letting Marshall do everything, they first give a different object representation and Marshall serialize that. So I use the same technique, more or less, but a bit more optimized. As a result, the size of the payloads were even more small than what I did for Mastodon, and even faster to reproduce. And so that's a patch that made it to Rails 7.1. So you will be able to upgrade and get it as well. And now we needed to fix it in Ruby, right? Because even though Rails was at fault, the behavior in Ruby was not good. Like not being able, like that the order is not very predictable is one thing, but being totally random is really problematic. So I let Aaron and Gemma know about the issue, and after some discussion, we agreed that the fallback implementation, the one that uses the hash internally, should use the ordered hash, whereas before it used the unordered hash. I'm not going to show the whole patch because it's C, so there's like tons more. The diff is way bigger than that. But what you want to see here is that before it was using an ID table, which is a hash implementation whose key are only symbols, and that's not ordered. And now it uses an ST table, which is what is backing the Ruby hash implementation. So now it's an ordered hash. And this was backported on the 3.2 branch. And whenever Ruby 3.2.3 is released, it should be usable. So what I think I learned on this bug or can be learned from this bug is that the big difference with the previous one is that it wasn't happening to me. The previous bug, I could observe it myself, iterate. I was able to really progress on it very, very fast. Here, it was much harder to debug because I could only hear what others said. I could ask questions, but then I would get answers hours later. It's a bit like helping your grandma on the phone debug a computer. It's very tiring experience. I couldn't simply just go in SSH in production and observe it myself. And so to me, this is like a huge advantage of open source, that you can directly debug yourself rather than do a back and forth with whoever sold you the software. And I think it's a major advantage. Another thing is like, be careful of Marshall. I really advise against using it. Like there's a valid use case for it, but be careful if you have a case where Marshall is going to serialize in one version of the application, deserialize in another. It can really lead to major issues. And not just with Ruby upgrades. Whenever you serialize an object in Marshall, if you change the name of variables inside that class, you will have trouble loading old records. So it's preferable to use more limited serialization formats, such as message pack or JSON or something like that. Another thing is like, or it might be easy for me to say, but don't be afraid to dig in lower layers. You will learn, worst case, you will learn so much. Like you just try to understand, like you have a bug with Marshall, try to go understand how Marshall works. It's intimidating, but there's really a lot to learn there. And finally, semi-deterministic behavior should be avoided at all costs. It's okay for something to be fully random. It's okay for something to be fully static. It's absolutely not okay for something to be deterministic until it's not. This is absolutely terrible. And so you shouldn't, like, if you observe such behavior, you shouldn't rely on it. Not every Ruby behavior is intentional and guaranteed to stay stable over time. Some things are implementation dependent and may behave differently on other Rubies or future version of MRI. That's all I had. Thank you very much, everyone.